The subject of my talk is relational mechanics, but it's very basic physics. So we go back to my greatest hero, Isaac Newton, which 300 years ago, he published the most important book in the history of physics, the Principia. And in this book, he did present his famous second law of motion and the law of universal gravitation. And we begin here with Newton's apple, okay? And the very simple... No. So with the free fall experiment, okay? That is just like that. So that is, in principle, the simplest experiment and problem in dynamics. We have a two-body problem, the apple and the ears, constant force, constant acceleration. So nothing else. So we just play Newton's second law of motion. The force is the weight of the apple, mg. We cut the two masses, and then we get the acceleration, which is capital G, mass of the ears, divided by the square of the radius of the ears. When we plug in the numbers, we obtain the free fall acceleration, 9.8 meters per second square. Everything is fine, except that this is not a two-body problem. There are stars and galaxies around the apple. Newton didn't know about the galaxies, but he knew about the stars. So we might say, oh, they are so far away, so we can neglect the force of the stars and galaxies. In principle, that's not true. The force of one star or one galaxy may be negligible, but when we add all of them together, they might have the same order of magnitude as the weight of the apple. They might even be infinitely larger if there are an infinite amount of stars and galaxies in the universe. So we must take them into account. In the textbooks, we don't, but the great Isaac Newton did. In his book, he considered his law of universal gravitation and considered a spherical shell of stars and the apple there. Then Newton proved a very important theorem, the most important theorem from cosmological point of view. I will read here Newton's words. This is Theorem 30 in the Principia. If to every point of a spherical surface there tend equal centripetal forces, decreasing as the square of the distance from these points, I say, Isaac Newton, I say that a corpuscle placed within that surface will not be attracted by these forces anyway. So Newton integrated the force exerted by a spherical shell on the apple. Just like here, the walls and the ceiling, they add up to zero. That only happens with force which falls as 1 over r squared. If it was 1 over r, 1 over r cubed, or any other law, this theorem would not be valid. And it is this theorem which allowed Newton to say that the force of the stars goes to zero. Only this theorem. Then Newton goes on and integrates for an apple outside the spherical shell. It might be the ears, for instance. And he shows that the ears will attract as if it were concentrated on its center. Okay? Now, with these two theorems, then we can go back to free fall. Then the forces acting on the apple, they are the force of the ears, then the force of the stars equals ma. The force of the stars goes to zero because of Theorem 30. Then, okay, now he obtains the acceleration of free fall. But it's not that simple. In principle, we cannot cancel these two masses. The mass of MA is inertial mass. The mass of the weight is gravitational mass. I cannot cancel them. The only reason why we can cancel them, it's another experiment, which was due to Galileo, which I can do it here as well. So we have two different bodies, just like here, a pound, a coin, and rubber, my apple. And if I release them, they go together, okay? It is this experiment which tells us that all bodies fall with the same acceleration, which allows us to cut the two masses here. And then we obtain that all bodies fall with the same acceleration. This is not a trivial experiment. For instance, two bodies fall with the same acceleration on Earth, but two electrified particles, they don't fall with the same acceleration in the same electric field. For instance, if I have a proton and an alpha particle in the same electric field, the alpha particles moves with half of the acceleration of the proton. So these two facts, they indicate that the inertia of anybody, of the apple and so on, it is related with gravitation, but not with electromagnetism, at least at the first level, okay? So now it seems that we have solved this very simple problem, okay? Two-body problem. Not yet. When we say that the apple falls with the acceleration of 9.8 meters per second square, that is the acceleration of the apple relative to what? Well, we might say, it's obvious. It is the acceleration of the apple relative to the ground. Newton said no. Why not? Because Newton utilized the same equation to study, for instance, the orbit of the Earth around the Sun. So the Earth is not accelerated relative to itself. So we might say, maybe it is the acceleration of the apple relative to the Sun. Newton said no. So what is it? Acceleration of the apple relative to the stars? Newton said no. So what did he say? Newton's words: absolute space without relation to anything external remains always similar and immovable. So this acceleration of 9.8 meters per second square is the acceleration of the apple relative to empty, free space. He gave a name, absolute space, but it is not related to the Earth. It's not related to the Sun. It's not related to the stars. It's empty, free space. So that is the words of Isaac Newton, the father of the baby, okay? So we need to accept his words. But Newton knew that this concept of empty space would be very problematic. People would not accept these ideas. How can you know the acceleration of the apple relative to empty space if you don't see empty space? Newton was so clever that he made a very famous experiment in which he proved that there is empty space without a vacuum pump. And the experiment, I will repeat it here because it is very famous. It was performed by Isaac Newton. He made it with a bucket of water. I'm Brazilian, so I brought Brazilian coffee. So prove it. It's very nice if you wish. So we have here Newton's bucket. The water or the coffee is flat. Then Newton rotates the rope here, and then he releases the bucket. That's the experiment, okay? The faster it spins, the larger the concavity of the water, okay? It is parabolic shape. So what's all about this experiment? How can you prove that there is empty space with these? There is not vacuum inside, it is air. So how can Newton prove that there is empty space? So the question which Newton wanted to answer, that was a real experiment, the first experiment which Newton presented in the Principia. It's so important that he put this experiment before his 3 laws of motion. It is this experiment which gives reason to about absolute space. So Newton wanted to understand why is the water flat here and then parabolic in the other situation. Well, we say, obviously, it is because here it is spinning, here the water is at rest. But the question is, the water is parabolic when it is spinning relative to what? So there are 3 material suspects. One is the rotation of the water relative to the bucket with whom the water is in contact. The other is rotation of the water relative to the ground. And the other is rotation of the water relative to the bodies in the outside, stars. So Newton said, in the beginning, both of them, they are at rest, okay? Then Newton spins the bucket. In the beginning, only the bucket moves, spins, but there is friction in the walls of the bucket. And then the water begins to rotate together with the bucket. So let us concentrate in this situation when both rotate together. So there is, Newton said, there is no relative motion between the water and the bucket here when both rotate together. So whatever is the force exerted by the wall on the water when they are at rest, the force is the same here because both are at rest relative to one another. So it's not rotation of the water relative to the bucket which creates this parabolic shape. So we might say, okay, it's not the bucket, but obviously it is the ground. Because here the water is at rest relative to the ground, and here it is spinning relative to the ground. But what is the force which the earth exerts on a molecule of water? That's Theorem 31. It is the weight of the molecule which points downwards. And when the water is moving like that, what is the force exerted by the earth on the water molecules? It is the weight downwards. The earth does not press the water sideways. It only pulls it downwards. And what about the stars and galaxies? Do you remember Theorem 30? The force which all of them exert on a molecule is 0 here. And when the water is moving like that, it's the same, 0. It's a theorem from Newton. So it's not rotation of the water relative to the bucket, not relative to the ground, and not relative to the other bodies in the universe. So Isaac Newton had no other choice but to say the parabolic shape is a proof that the water is rotating relative to empty space. It is just fascinating, this experiment. So the omega here is the angular rotation, according to Newton, is the angular rotation of the water relative to absolute space, that is, relative to empty, free space. Then, 200 years later, came a very famous physicist, experimental physicist, known as philosopher, but he was an experimental physicist, Ernst Mach, and Austrian physicist, and he published a very famous book which had a huge influence upon Einstein. And in this book, 1883, Ernst Mach said the following: "The principles of mechanics can be so conceived that even for relative rotations, centrifugal forces arise." Or, try to fix Newton's bucket and rotate the heaven of stars, and then prove the absence of centrifugal forces. This, I will make a question to all of you. and I will give you 1 minute to answer me. I will wait in my watch here. Think about that. It's a thought experiment, okay? You don't need to be afraid of your answer, because we don't know the answer. And we will never know the answer, because we cannot perform the experiment which I will talk here now. So suppose that in Newton's real experiment, the water rotates once a second, and it goes up to the rim of the bucket. If I rotate faster, it spills out of the bucket, okay? Once a second, it goes up until here. Now, I let the water at rest here on the table. And the Superman goes there in space and rotates all the universe around the axis of the bucket. Once a second. What will happen to the water? So we don't know the answer, and we will never know. And anything can happen. It can explode. It can be a transmutation. It can transform into gold. But there are 2 main questions that I want you to pick up, each one of you. Either it will remain flat, or it will become parabolic. So think about that, and in a minute, I will ask you to raise your hands. Really, just wait a moment. Think, each one of you. Think, then I will give you the 2 options. And I want each one of you to choose one of these 2. So the first option, raise your hands, because what you choose, I will know if you are your point of view. Okay? Those of you, please, raise your hands. Those of you who think that when I spin the whole universe once a second around the axis of the bucket, that nothing will happen to the water, that it will remain flat. Okay? Now, those of you who think that when I spin the whole universe, that it will become parabolic. So I would say that 2/3 of you think that nothing will happen. And 1/3, maybe a little less, 1/4 of you think that it will become parabolic. So that is the question, okay? What will happen if I spin the whole universe around the bucket? The majority of you said that nothing would happen. So you are Newtonians. Yes, really. That is the answer which comes from Newtonian mechanics. Ernst Mach, on the other hand, he said, the relative rotation is the same. It doesn't matter if I spin the water or the universe anti-clockwise. So if the relative rotation is the same, the effect must be the same. Unfortunately, we cannot make the experiment. But you see, this is so important that here are the words of Einstein. Just a minute. In his book, The Meaning of Relativity, he said the following: what is to be expected along the line of Mach-Shot? A rotating hollow body must generate inside of itself a Coriolis field and a radial centrifugal field as well. You see, Einstein wanted to implement the ideas of Ernst Mach. He liked them. You see, Ernst Mach had this idea that it must happen the same way, but he didn't prove it. He didn't prove experimentally, because that is impossible, but he also didn't prove it mathematically. Newton had shown that there is no force of the stars on the bucket. But Einstein said, if Ernst Mach is correct, somehow when you rotate a spherical shell, it must generate a real centrifugal force, which will make water goes like that. However, when you do the calculations with Einstein's general theory of relativity, I won't show the details here, you have a centrifugal force, but there is also a component along the direction of the axis, so it doesn't become parabolic. Einstein didn't like this. He wanted it to be like that. But in his theory, at the end, it didn't work out. But you see, this experiment is so important for Isaac Newton, for Ernst Mach, for Einstein. Go back to your home, to your countries. Think about this experiment, because it is the deepest experiment of classical mechanics. Very simple to perform, but the interpretation, the consequences are extremely deep. So, in the second half of my talk, I will talk about what I call relational mechanics. It's a book which we published, it's in our homepage. So relational mechanics is based on two postulates. Instead of Newton's second law of motion, we say the sum of all forces acting on any body is always zero in all frames of reference. And instead of Newton's law of gravitation, we have a Weberian force law for gravitation, the same which I talked yesterday. So if Weber's law is so powerful, you deduce Faraday's law of induction, Ampere's force, telegraphy equation, wave equation, conserves energy, and so on, why not apply the same for gravitation? So that's the idea. And the first postulate, I say, that the force on the apple is zero when it goes up, down, in my hand. If I were a worm eating the apple, I would say that the force would be zero as well, all the time. So, that's crazy. So, what I want to show here is the main difference between Newton's law of gravitation and Weber's law for gravitation. So the question is, I am inside a room like a spherical shell. What is the force of the walls and ceilings of this room on the apple when I accelerate it with my hand, just like here? So Newton, as I showed, Theorem 30, it's zero. But Theorem 30 for Newton is valid for a component which falls as 1 over r squared. So the velocity component also falls as 1 over r squared. So it also goes to zero. But the last component, there is a r here, which cancels, so it falls as 1 over r, just like Faraday's law of induction. So when I integrate that, it is not zero any longer. When I integrate that, the force, gravitational force exerted by the shell on the apple inside is minus phi ma. So now I can solve the problem of free fall with relational mechanics. I said that the sum of all forces on the apple is zero. So the force of the earth is essentially Newtonian law, because velocity and acceleration are small. But the force of the whole universe on the apple is no longer zero. When I integrate that, it will be minus a capital phi ma. So this is Newton's second law of motion. We are deducing Newton's second law of motion instead of postulating it. So here it is the essence of relational mechanics. So the previous slides presents the essence of relational mechanics. We begin with the postulate that the sum of all forces acting on any body is always zero. Then we deduce an expression analogous to Newton's second law of motion, F minus ma equals to zero. In this equation, F here represents the usual forces acting on the apple, gravitation, electric, and so on. The expression minus ma represents a real gravitational force exerted by the set of distant galaxies acting on any test body according to Weber's law of gravitation. The mass appearing here is no longer the inertial mass of Newtonian mechanics, because it comes from Weber's gravitational force law. So it is already a gravitational mass that you can cancel with mg. And the acceleration which appears here is no longer acceleration relative to empty space. In relational mechanics, it's acceleration relative to the frame of distant galaxies. So I showed to you, this is the force minus phi ma when the shell is at rest and the apple is accelerated inside. What happens if I spin the spherical shell? So that is the next result, which is here. So the force by Newton's law of gravitation, it would remain zero, always zero. That's Theorem 30 of the Principia. But with Weber's law, it's no longer zero. When I integrate the force exerted by a spinning spherical shell on a test body which is moving inside the shell, I obtain the previous result minus phi ma, but there is also a real centrifugal force and a real Coriolis force. So you might, those of you who have studied mechanics, remember these two components. But in Weber's law, they are not fictitious. They are real forces of gravitational origin. So let us go back to our famous bucket experiment. What does it, relational mechanics, gives? What is the shape of the water? So this is the expression of Newtonian mechanics. This is the parabolic shape. Square, angular rotation is square, and the gravitational field of the Earth. There is nothing about the stars here. And this is the result of relational mechanics. I don't show the details of the calculations, but the main difference is that what appears here is the relative rotation between the water and the set of distant galaxies. In Newton's real experiments, these were essentially at rest. So I spins only the bucket, and it becomes parabolic, just like that. And here, now this is the result of the thought experiment. The water is at rest, and then if I spin the universe once a second, mathematically we obtain the same parabolic shape. So that is the essence of the theory. Can we make tests about this theory? Yes, we can make tests. For instance, I go in the outside and measure the acceleration of free fall of the apple, just like Newton, and I obtain 9.8 meters per second square. Then I bring the apple inside of this room. What will be the free fall acceleration? Well, depends on the theory and on the experiment, obviously. If we calculate with Newtonian mechanics, Theorem 30, it doesn't change, 9.8. Einstein wanted the acceleration to be smaller, but in his general theory of relativity, the same result of Theorem 30 of the Principia is valid, so it doesn't change. In relational mechanics, on the other hand, it will be 9.8, 1 minus a very small term. The problem is, if I have 1 meter radius spherical shell, 1,000 kilograms, that will affect almost nothing. It will be smaller, but so smaller that I cannot measure that. But you see, it's not the same prediction. Can we make another test? Yes. I cannot spin the whole universe around the bucket, but I can put a glass shell around the bucket, and I can rotate only the glass shell around the axis of the bucket. Okay? Why can't we do the experiment? Obviously, we can do the experiment. What happens? I will first show you the theory. The theory is the following. According to Newton, nothing happens. According to relational mechanics, it should be parabolic. According to Einstein's general theory of relativity, there is this wiggle in the middle. Very strange, but that's what comes from Einstein. The problem is the order of magnitude. Can we measure that? Not at all. If we have 1,000 kilograms, and if I spin that, the factor, this k here, it's 10 to minus 24. That is just nothing. The water, they will go up, not even an atom. It will go up 10 to minus 27 meters. That's nothing. So in principle, the answer is different. The problem is that gravitation is so weak that the effect in the laboratory, we cannot measure that. So essentially, it will remain flat. So, in conclusion, these are the two postulates of relational mechanics. The sum of all forces on the apple, everybody, is always zero. Instead of Newton's law of gravitation, Weber's law for gravitation. What we deduce with this theory, we deduce Newton's second law of motion. We do not postulate that. We deduce the equivalence principle, that is, that the mass which appears in MA is a real gravitational mass. We show that the centrifugal and Coriolis forces are real forces of gravitational origin exerted by the set of distant galaxies. And there is a quantitative implementation of Mach's principle. Thank you.